So good morning, my students. Matrices Part 3. So in trace of the matrix, I forgot to give some properties. See here, trace of A plus B is equal to trace of A plus trace of B. Trace of A minus B is equal to trace of A minus trace of B. Trace of K into A is equal to K times of trace of A, where K is some constant. And trace of AB is same as trace of BA, but it cannot be written as trace of A into trace of B. Okay, so trace of A plus B is equal to trace of A plus trace of B. Trace of K into A is equal to K times of trace of A. Trace of AB is equal to trace of BA, but it is not equal to trace of A into trace of B. Next to definition, transpose of a matrix. So transpose of a matrix capital A is denoted by A dash or A transpose, A power T. But I am using the symbol dash. Okay. So how we can obtain A dash? Just interchange the rows and columns of the matrix. Just interchange the rows and columns of the matrix. So that means if the order of A is n by n, then order of A dash, its transpose must be n by m. Here I have taken one example. It is a matrix of order what? 2 by 3. It is a matrix of order 2 by 3. Obviously its transpose must be what? 3 by 2. So what is the first row? 1 4, second row 2 5, third row 3 6. And also these are the properties on the transpose. A dash whole dash is equal to A plus B whole dash is equal to A dash plus B dash. If this minus is there, minus is there, minus. That is A minus B whole dash is equal to A dash minus B dash. K into A whole dash is equal to K times of A dash, where K is some constant. And AB whole dash is equal to B dash into A dash. These are the properties on the transpose of a matrix. Next definition, conjugate of a matrix. So we have heard this conjugate word in complex numbers. So what is the conjugate of A? If A is a real number, then the conjugate of A is itself. If A is a non-real number, conjugate of A is denoted by A bar. So thus what is A bar? Suppose if I take A is equal to 1 plus 2i, then conjugate of A bar is equal to 1 minus 2i. Because the conjugate of iota I is minus I. But the conjugate of any real number is itself only. That is conjugate of 2 is 2, conjugate of root 2 is root 2, etc. So how to obtain conjugate of a matrix? What is the conjugate of a matrix? So if capital A is a given matrix, then conjugate of A is denoted by A bar, and that can be obtained by replacing the elements of A by their respective conjugates. For example, capital A is equal to 1 plus I, 2, 3 minus I, and only I. Then the conjugate of A is denoted by A bar. So it can be obtained by replacing the elements of A by their respective conjugates. 1 plus I conjugate is 1 minus I, 2 conjugate is 2, 3 minus I conjugate is 3 plus I conjugate is minus I. Then the transpose of this conjugate is called transpose conjugate matrix. The transpose of this conjugate matrix is called transpose conjugate matrix. And remember, the transpose of conjugate of a matrix is same as conjugate of transpose of the matrix. That is, A bar whole dash is same as A dash whole bar. And it is denoted by A power theta. What is A power theta? It is the transpose of conjugate of a matrix or conjugate of transpose of a matrix. So, for the above example, what is A power theta? So, if A is this matrix, what is A power theta? Then first you find conjugate, then find a transpose. Or first you find a transpose, then make it conjugate. So first I find here conjugate, make it a transpose. What you will get? 1 minus I, 3 plus I is the first row. And second row will be 2 minus I. So if A is this matrix, then A power theta is this. What is A power theta? Conjugate of transpose matrix or transpose of conjugate matrix. So next important definition is a symmetric matrix and skew symmetric matrix. So a square matrix capital A is said to be symmetric matrix if A transpose is equal to A. A transpose is equal to A. Then what do you say? A is a symmetric matrix. So that means what is the meaning of this definition? After interchanging the rows and columns also, the matrix is, whatever you are getting, that matrix is same as given matrix. That means it is possible only when corresponding row elements and column elements must be identical. Then only that matrix satisfies this condition, and hence that matrix is called symmetric matrix. Okay? Suppose if A dash is equal to minus U. If A dash is equal to minus U, then what do you say matrix A? Skew symmetric. A square matrix which satisfies this condition A dash is equal to minus A is called what? Skew symmetric. Or we can call like this also. A square matrix is said to be skew symmetric if A dash is equal to minus A. A dash is equal to minus A. Okay? So A dash is equal to minus A. From this condition, what we can say that, so the diagonal elements of skew symmetric matrix is always 0, are always equal to 0. Remember, the diagonal elements of skew symmetric matrix are always equal to 0. And Aij is equal to minus Aij. Of course, from this condition only what we can write? Aij is equal to what? Minus Aij. Okay? So Aij is equal to minus Aj. Sorry. Minus Aj. In case of diagonal elements, I is equal to j only, na? So if you take I is equal to j, you will get diagonal elements. Aii is equal to minus Aii. After simplifying this, what you will get? Aii 0. So thus the diagonal elements of skew symmetric matrix are always equal to 0. Okay. So remember example for symmetric matrix 1, 2, 3, 2, 3, 4, 5, 6, 5. It is an example for symmetric matrix. And skew symmetric matrix, diagonal elements must be equal to what? 0. Here if I take 1, 2 here, in first column what I will take? Minus 1, minus 2. And here if I take 3, this will be minus 3. So for this, if you find transpose, it is same as minus A. If you find transpose, it is equal to A only. It is an example for symmetric, and it is an example for skew symmetric. And some properties on symmetric matrices, symmetric and skew symmetric matrices. It is an useful properties. Try to remember these properties. Suppose if A is a symmetric matrix, then the matrices minus A, K into A power n, A transpose, A inverse if it is exist, and B dash A into B are also symmetric. If A is a symmetric matrix, then all these matrices also symmetric. Here K may be any real number, here N may be any natural number, and here B is a matrix of order that of A. Okay. Similarly, if A is a skew symmetric, then K into A transpose, B dash A, B are also skew symmetric. Okay? And if A is a skew symmetric matrix, its power if it is odd number, suppose A power is 2n plus 1, A power is 2n plus 1. So then it is also skew symmetric. If A is a skew symmetric, A power or any odd natural number is also skew symmetric, and A power any even natural number is symmetric. A power any even natural number is symmetric. Though A is a skew symmetric, A square, A power 4, A power 6, A power any even natural number is again symmetric, and A power 2n plus 1 is skew symmetric. In skew symmetric, you have to remember one more important point. Determinant of skew symmetric matrix of odd order, it is always equal to 0. Okay, determinant of skew symmetric matrix of odd order is equal to 0. It is important point because based on this point I have seen many KCET problems. Okay, as determinant is equal to 0, then it is singular matrix. It is a singular matrix, and hence A inverse does not exist. That means A is not invertible. Okay, skew symmetric matrix of odd order determinant is 0 implies that it is singular matrix, implies that inverse does not exist, implies that A is not invertible matrix. Okay, but if it is even order, then the determinant is square of some real number. It is a square of some real number. Okay. So that means determinant of skew symmetric matrix of even order, it is not equal to 0, but it is a square of some real number. Next important point. Suppose if I take two matrices, suppose A and B, two symmetric matrices, then A plus or minus B, A plus or minus B, AB plus BA is also symmetric, but AB minus BA is skew symmetric. This is the third point. Next, fourth point, if A and B both are skew symmetric, then A plus or minus B and AB minus BA are also skew symmetric. But AB plus BA is symmetric. Then what you observe from these 2 points? So if A and B both are symmetric or both are skew symmetric, AB plus BA is symmetric, AB minus BA is skew symmetric. Okay? But if A is symmetric, B is skew symmetric, then AB plus BA will be reverse. It will be reverse, skew symmetric, and AB minus BA becomes symmetric. Okay? If A is symmetric, B is skew symmetric. One is symmetric, other one is skew symmetric. Then these two becomes reverse. AB plus BA becomes skew symmetric, AB minus BA becomes symmetric. Next important point. So for any square matrix A, A plus A dash, it is always symmetric, and A minus A dash, it is always skew symmetric. Okay? And also, one more important point, every square matrix can be represented as a uniquely sum of symmetric and skew symmetric. See, if you simplify half into A plus A dash plus half into A minus A dash, what you will get? A. And from above, A plus A dash is symmetric. Then using K, if A is symmetric, K into A is also symmetric. So A plus A dash is symmetric, half into A plus A dash is also symmetric. A is skew symmetric, K into A is also skew symmetric. A minus A dash is skew symmetric, means half into A minus A dash is also skew symmetric. So every square matrix can be represented as a sum of symmetric and skew symmetric, and this representation is unique. Okay, that means the symmetric part of capital A is half into A plus A dash, and the skew symmetric part is half into A minus A dash. And previous year problem, suppose same model, not the same problem. Suppose A is equal to 1, 2, 3, 4. It is equal to B plus C. It is given that where B is a symmetric and C is a skew symmetric. B is symmetric, C is skew symmetric. Then what is the matrix B? So just what you have to calculate, B is nothing but a symmetric part of A. Symmetric part of A is what? Half into A plus A dash. So if you simplify, I think 1, 5 by 2, 5 by 2, 4. You will get this matrix. Matrix B is this. So this is the previous year mains model problem. Okay. Next, last important point. Suppose A is a skew symmetric. Of order n. And suppose capital C is a column matrix of order n by 1. Then C dash AC. Okay, C dash AC. It is always skew symmetric. And it is equal to null matrix. And one more important point. Null matrix is the only matrix which is both symmetric and skew symmetric. Okay. Thank you.